Okay, hello everybody and welcome to this session on implementing OpenGL ES on an embedded device. My name is Petri Kero and I've been working for hybrid graphics for the past 5 years, being involved in different kinds of software, computer graphics projects, and the most recent one being the OpenGL ES implementation that we made, and I was the lead architect for that. I'll first be speaking a bit about the state of the mobile graphics industry in general, having a bit of a focus on mobile gaming, and then introducing Kronos Group to those who don't know that already, what they are up to and what they have done in the past, like the OpenGL ES standard. And then finally we'll get into the good stuff, like what we learned during the course of the implementation of the OpenGL ES project. Okay, so what are the main application areas for 3D graphics, especially in the embedded space? Well, of course, everybody knows games and screensavers that are already pretty common on mobile phones and PDAs, and we've also seen some Tamagotchi kind of virtual pets and UI components, all sorts of things. And then in the automotive industry, there's a pretty big pressure on getting the infotainment system, which basically means the radio. That's all those guys know, it's the radio. It's always radio, no matter if it's the navigation system, but their mindset is that it's always the radio expanding into everything else, and that's about it. And then in aviation, well, you have all seen in the movies the tunnel in the sky effect, the instrumented landing system. And of course, military has its own applications, but if I told you, I'd really have to kill you, so we'll skip that one. So what is a mobile device really as a gaming platform? How does it differ from the desktop computers? Well, the primary difference is, of course, that it's really mobile, like the name says. You always carry it around with you, like when you're on train commuting to your work or school, when going to a summer cabin, everywhere. Laptops are pretty mobile as well, but not nearly as mobile as your cell phone. Another big difference is that they're always connected to the network. You could argue that the same applies to most computers, and that's true, but there's a really big difference in laptops as well, because usually when you grab it with you and hop into your car, you almost always disconnect it. Of course, there's GPRS, but well, you all know how that works. Another thing are the new interesting input and output devices. Like there are already location-based games that are played in Japan. You have cameras that you can use to control. One really interesting thing was the game called Marble Madness, which was implemented using gyroscopes. And well, Nintendo DS has the multiple displays. Another thing making mobile games successful is the micropayment revenue model. The thing is that how it separates from the desktop, where you could argue that it's also there, but in mobile space it's really handy. Everybody's already a customer of some operator, so they're also a customer of a micropayment payment system. Whereas on the internet you always have to take your credit card, and it's a big hassle there. And from gaming perspective in specific, the devices are getting really powerful. We're already approaching the 96, 97 desktop level, so that we are getting hardware acceleration on things like the Gizmondo and so forth. And from business point of view, maybe the most interesting thing is that these devices are truly mass market, whereas the consoles or PCs are not, at least in comparison. Now, what I mean by mass market is that there are already billions of devices out there, and last year alone, more than 600 million new phones were sold. So that's something like 20-fold to times of games consoles being sold. So it's really a dramatic number. And I believe there were something like 140 million PCs sold last year. And the thing in comparison which is also making these devices popular is the fact that they are subsidized by the operators, quite similarly as Sony subsidizes their PlayStation. So where's the money, you might ask? Well, there's a really easy, maybe a bit naive formula for computing the amount of dollars that's actually moving in the business, and you can count it by just multiplying the number of devices out there, the number of games both per average number per, like anyone owning a mobile phone, and then multiply that with the cost of the game. And well, we all know how that the games on phones are cheap, maybe something like 10 to 20% of those of the prices of console games, and the amount of people who actually play on their phones is really small. But again, it boils down to the number of devices out there, and we're doing everything we can to make this a successful business. So how does hybrid relate to all this? We've been in the computer graphics industry for the last 10 years already, almost 11 now. We are a mostly engineering company consisting of 30 people, most of which are engineers, around 23 I guess at the moment. Most of the guys at the office are old demo scene hackers and been involved in different games companies, and well, of course we're always looking for new talent if anybody's interested. And the primary thing that we do is to design and implement open standard APIs, and I'll come into that in a short while. The other stuff that we do at the office is academic research, like writing papers to different conferences. Some might know there's SIGGRAPH coming up right next week, and I believe there's at least one paper with an author from our company, and then different white papers, consultation, and so forth, even a bit of hardware design. What we would like to do is to get the games industry go mobile, and the way we thought that we could help in the process is by letting the games developers concentrate on what they know best, which is making games, of course, instead of the current situation where they are just banging their heads on different technological walls, like porting their stuff to different platforms and so forth. And our action to do this is to provide core graphics technology. And we do that by making implementations of different graphics APIs. You can see a list there, like OpenGL ES, OpenVG, different Java APIs, so forth, even vector graphics. And another way for us to contribute into all this is to actively participate in all kinds of standardization efforts that there are going on in the world, most notably Kronos and different Java community processes. And we plan to actively support all devices from pure software into full 3D hardware acceleration. Why standardize? We believe that standards are good for everybody. For developers, well, they need to target a dozen different devices, and they really have tight budgets, so it's really a burden for them to actually implement a game engine, graphic engine, and then port that to all different kinds of devices, and maybe even different programming languages, and they can be helped by having the standard APIs already in the platform. Another party to benefit from this is device manufacturers, because that's the way they get their devices sold. You need to have some new cool technology in your platform in order to sell it, and graphics is one of those. And of course, buying proprietary stuff, which means non-standard, would tie the device manufacturer into one single component manufacturer, and that's a bad thing for them. And of course, the IHVs, the hardware manufacturers, benefit from from faster adoption, which we get from avoiding the API wars that we had on PC, OpenGL against Glide, against 3D3, so forth, and that of course means more chips sold to them. The most relevant standardization efforts that are going on in the world, at least from our perspective, are the native APIs being developed by Kronos, OpenGL ES and EGL, plus there's the OpenVG vector graphics API, 2D API coming up. The first version of OpenGL ES was released already in 2003, and the ES stands for Embedded Subset of Desktop OpenGL. And there are a number of new improvements coming next week. In SIGGRAPH, ES 2.0 is going to be released. It's going to be a pure API with full shader support, and actually all the features that can be implemented using shaders have been dropped from the fixed function side. So you cannot set your texture combine modes anymore, but instead you write your shader to do that. And of course, Kronos helps the adoption of the standards by providing conformance tests and adapters package, which also keeps the quality bar higher than on desktop. On Java side, there's the M3G, also known as JSR 184, which is a higher level API and kind of scene graph based, which is currently, I guess, the most actively used in games development. And then there's the upcoming JSR 239, which is Java bindings for OpenGL ES. Kronos consists of, actually today, nearly 100 top companies in the computer graphics industry, and it's divided into two member groups. The outer ring is the so-called contributors, who are doing all the work on actually creating the specification and making all the decisions on which features to include and which ones to leave out. And then in the inner ring you can see the promoting members, who basically consist or form the board of Kronos and make all the higher level decisions, like which APIs to actually include inside Kronos, and once a working group has finalized their specification, then it undergoes a ratification voting by the promoters. They also decide the budget. The way OpenGL ES differs from desktop OpenGL is that it's a really lightweight subset of its parent spec, and it's been created with full blessing and cooperation from the ARB, which stands for the Architecture Review Board, the body behind the OpenGL standard. And the biggest difference is that we are aiming for really low code footprint. We are talking about around 100 kilobytes in code size, whereas I guess desktop drivers are multiple megabytes and so forth. And hardware implementations need to be really small. We're talking about hundreds of thousands of gates instead of tens of millions, and of course power consumption is an issue, and well, there's wildly differing displays from black and white, really small areas, to VGA and even beyond. And we need to keep in mind that the OpenGL ES spec is not standalone, but it's kind of like a different specification to OpenGL, so that it only specifies where it differs from OpenGL. But still, it retains all rendering features and only tries to eliminate redundant or duplicate and legacy functionality that we didn't believe that is really needed, even in desktop OpenGL, or at least in the mobile world. So other things that got removed, well, there are a lot of variants, for instance, for setting, let's say, the current color of OpenGL state, and I guess there are at least a dozen variants for that function, and we ripped all of those out except maybe one or two depending a bit on the situation. And some of the higher level features that got dismissed were, for instance, display lists, evaluators. We believe that those can be easily implemented on top of OpenGL ES, and they don't need to reside inside the implementation itself. And there hasn't been that much use for those features anyway. Other things are pixel rectangles. You can implement those using textures. Stippling can be done using textures, and so forth. Some texture formats were also removed. And a really, really major thing that happened was that the ES 2.0, which is coming out next week, we threw the whole fixed functionality pipeline out, and finally we did that. It's been dragging along so long there that, well, progress has been done now. Anyway, other changes to ES 2.0 compared to OpenGL is that some of the more complex features in the shaders were still left out because of size and power consumption reasons. There's also some new stuff that we had to add into the embedded subset in order to make it work on mobile systems. And one of those was the fixed point entry points, so that whenever you could call something like GL frustum with a floating point parameter, you can now do it with fixed point as well. And that's because usually none of these devices really have FPUs in them. But keep in mind that it's only in the ES 1.x track, and the 2.0 won't be having those anymore. And then we added byte fixed point data type for the vertex data. Some of the OpenGL calls are double precision only. Single precision variants were introduced in place of those. The conformance tests themselves have been made more rigorous. Also, the process is a lot stricter for implementers, because previously there was no process of actually checking that if somebody is conformant or not, but now there's a peer review process. Another major thing is that EGL, which is the Wiggle or GLX equivalent for ES, it got standardized this time, so there's less porting work whenever going to a new platform. And in ES 2.0, there's added support for offline shader compilation, and actually we also removed the requirement that the compiler actually has to be present on the device, so it's sufficient for only having it on your PC and compiling everything beforehand. Sorry? Well, yeah, the question was that why were the fixed function entry points removed, and the answer is that we believed that those weren't needed anymore. The fundamental idea behind that was that we don't want to introduce duplicate functionality. There's shaders for doing that, and we believe that it's a lot more pure way of actually doing things. So the fixed function would only have been in the way, and it actually causes quite a lot of implementation burden, because you have to interface between, let's say, a fixed function vertex pipeline and a programmed pixel pipeline. So here's kind of our view of where OpenGL ES sits in the food chain, so that it's kind of built on top of the operating system, the CPU, and there might be some multimedia accelerator like a DSP chip from, let's say, TI present, and maybe even GPU, which of course could be considered a part of the ES itself. And then one fundamental difference that we made compared to other manufacturers of these APIs is that we've actually separated the higher level APIs like JSR 184, which is the Java high level API. We totally separated it from the ES layer, so that we can actually plug and play or improve the performance by just replacing our software implementation with the hardware one if available on some platform. But of course, many platforms still just don't have hardware in them yet. And of course, middleware and games can be you can use the OpenGL ES directly, or if they're made in Java, then through the 184 or 239 APIs. The core team of the project itself consisted of typically 5 to 6 people at any given moment, a bit less at the beginning and in the end. And everybody on the team had already a pretty decent background in computer graphics and typically even also in software rendering. And at the beginning of the project, we actually picked kind of like a specialization area for everybody working on the project, so that people could get a chance to do something that really interests them, and also we could kind of cut down the communication burden inside the project, so that each person would be responsible for their own field there. And we had specialists, for instance, for like compiler technology, arithmetic operations, and I was responsible for the actual rendering pipeline implementation. And this was already our second OpenGL ES implementation. The first one that we made, we sold all the rights to our customers, so we really had to build it from the scratch. And overall, this is something like our 14th or so rendering engine. So we really have a past in that area. The basic technology, like it says on the board, took us about a year to implement, consists of 150,000 lines of code, and even though we consider the project more or less finalized so that it's complete, it's still going on in many ways, because we're adding support for new versions of the specification, like ES 1.1 came out last year, and this year Kronos will be introducing an extension package on top of the 1.1. And other things that we've been working on it is that, well, new optimizations, you can never be fast enough, of course, and integration into new platforms. So what makes this all so hard? Why even talk about it? Well, you can see the list of different difficulties that we faced, or challenges that we faced during the project, and I don't think any of those really is that big in itself. But all of those combined at the same time really puts a lot of pressure on actually building the implementation. Well, the reliability is one of our main goals, or has been one of our main goals during the project. The device manufacturers and, well, even the end users or developers, or, well, basically nobody likes it if our software crashes. Well, that's no news to you, of course, but in a mobile phone, you really, once you ship, you cannot go back. It's often impossible to actually update the software that you put on the phone, because it might be in the ROM of the phone, or otherwise it's going to require at least a visit to some shop which can actually, or has the equipment to do the updates. And of course we really must conform to the standards that we claim to implement, or otherwise it's just impossible to really write portable games on top of such an implementation. So how we accomplish this is by testing from day one to, well, up until now, and continuing into at least the foreseeable future. We've spent something like 80% of our development resources on building different testing frameworks, testing tools, internal self-validation, and the testing process in general. Oh, did I mention testing? Anyway, we have three main ways of testing the implementation, and one of those is the conformance test originally built by SGI, and now under the Kronos control which you have to pass if you want to use the OpenGL ES logo, so that the logo is kind of like a quality mark for your implementation, but it really doesn't guarantee that much. Too bad, but that's the situation. Well, on top of that, we had another testing suite called the Visual Tester, which was mainly used during the development of the implementation, and it's good for doing cross-comparison between different implementations. Like we always compare it to, let's say, NVIDIA's or ATI's, or well, lately mostly using Mesa, because that just seemed to be the most stable OpenGL implementation out there. But we got a good reference from those, so that we knew that we were doing the right thing, and we just didn't have to think everything from scratch, like, is this the right pixel here, but we can just cross-compare. And currently, the most kind of testing that we do is stress testing and regression testing. We have basically a farm of PCs, and the developer PCs that we have, they're all running different kinds of testing suites all the time, which basically consists of different kinds of randomized stability tests. And the point of those is that because they are random, we really can reach all the different code paths in the project, and we have verified this using code coverage tools. And these, combined with a lot of self-validation and different memory checking tools like valgrind, for instance, or page heap, gives us a really, really good confidence in the project that it just doesn't crash anymore. There are no memory leaks. We don't corrupt any memory that we aren't supposed to, and so forth. A lot of the quality also comes from the processes that we used during the course of the development. And one good way of actually getting some extra quality into your software is to use multiple compilers at the maximum warning levels. You, of course, well, almost all of the time you get false alarms, but every once in a while you get a report of a real bug in the form of a warning, and it really pays off. And of course, Lint is another good program for doing such static analysis. Some other things that's included in our processes are code review. We do it both in-house, and we let our customers review our code. That brings up some bugs to the surface every once in a while. And by just using rigid coding processes in the sense that you always use specific design patterns and so forth, you make it hard for yourself to make mistakes. You don't want to be allocating memory in shady places, but you always want to do it in the constructor and release it in the destructor or so forth. Just use good processes. And benchmarking is also really important. At least we consider all performance problems to be bugs as well. Often they are like true bugs, so that you have actually ended up blitzing your screen twice. It really doesn't hurt anybody otherwise than poor performance, but well, it's a bug anyway, and it should be fixed. And also post-integration benchmarking is really important, because there are a lot of things that can go wrong in an integration process. Portability is a tough one. Has anybody in the audience ever programmed anything for Symbian? Okay, so add a dozen of those platforms, but even worse, and you know what we've been facing in the past. Well, that's all I'm going to say about that topic. The thing is getting better, at least slowly. A lot of kudos to Symbian for actually including a lot better tools in the upcoming versions of the operating system. They'll be using RVCT as the main compiler on Symbian 9.x, I believe. So, some of the problems that we've been facing during the porting is mainly caused by bad compilers or other bad tools. And for instance, we've seen cases where just switching the compiler has actually given us like a 2 times performance boost, which I consider dramatic, and it's such a easy trick to do, because getting that sort of optimization results could easily take months or even years. And well, we've been forced to kind of enter into a certain hack mode at times, just to avoid the problematic compilers. So that, for instance, when we compile for Windows CE, that's one of the systems with one of the worst compilers actually. We are not using the compiler that they are providing, and the problem there is that they're not making it easy for us, because the object files themselves aren't really compatible with anything else. So we just cannot use another compiler and then link the object files into the same project. But rather we had to use RVCT in this case, take the disassemblies out of that, then build a Perl script which actually takes the disassemblies, converts those into the format understood by the WinCE assembler, and after that we were able to get the performance that we wanted. So things might get a bit dirty every once in a while. And well, another thing is that just don't try to be clever. Don't even use C++, because it's not going to work on many platforms. There just simply aren't C++ compilers for some platforms. The things that make it hard for us to actually provide a well-performing implementation is, well, first thing is, of course, slow CPUs. It's kind of hard to make anything run fast on a slow CPU. But in addition to that, we are also facing the lack of floating point units, which is pretty dramatic, because the OpenGL ES common profile actually requires you to support not exactly the IEEE floats, but something comparable to that. So we had to go through different tricks and hoops in order to get good performance with those. The cache architectures are also often, or might be a bit weird. Well, fortunately in the ARM9s that we see mostly today, that's starting to be resolved. And one big thing is that a lot of the CPU time might be consumed by something else on the phone, like maybe communicating with the baseband network, or I don't know, playing sound, which doesn't take any time on a PC anymore, and so forth. And it doesn't help us at all, because profiling is so goddamn difficult, because there really aren't those tools available that you'd like to use. Like, for instance, on PC you can just run vTune, and it's almost perfect tool for actually profiling your software and seeing where the bottlenecks are. But due to the differences of the ARM architecture to x86, it's just, well, those give some kind of an idea of where the time is being spent, but still there are big differences. Also, there should be a lot more benchmarks out there. SPMark is really good, but it's only on one platform, at least at the moment. JBenchmark, well, also pretty good, but only runs in Java. So in the end, you just have to roll your own synthetic benchmark and use that one to get a good idea of where the time is being spent. The specific tricks that we made to actually make our implementation well performing is to, well, in addition to the standard tricks like using vertex caches and carband clipping, we tried to push every possible culling operation, like let's say backface culling, view frustum culling, as early in the pipeline as possible, and move everything else into as far in the pipeline as possible. For instance, viewport transformation, lighting, fork, texture matrix operations, and so forth. Many of these are even done after the scan conversion, which gives us pretty good results on very small polygons. Perspective correction has always been a bit problematic in software rasterizers. We solved that one by using tessellators, because those basically give you an algorithmically better performance than, let's say, an every pixel or every n pixels correcting algorithm, and it gives you a really good and smooth result compared to the n-pixel variants. Also on the pixel pipeline side, you want to do as many early exits as possible and as early as possible, like doing def test before texture fetching and trying to do all the, let's say, stencil tests and whatnot as early as possible again. Perhaps the most challenging area for us was the pixel pipeline. I guess many of you already know that it consists of a number of states, and if implemented in a really naive way, you would have to actually do, I don't know, maybe 20 or 30 or even more like switch cases there to see which def test mode you are using and which texture combine mode you are using. Are you using bilinear or just point sampling? All sorts of states. And it's pretty hard to deal with that one in a well-performing way. And the approach that we chose, we've been using stitchers in the past so that you kind of have these small bits and pieces of assembly code programmed by hand and then just taking those pieces and stitching the proper loop together. But this time we wanted to go a bit further, and we actually implemented a compiler inside the OpenGL ES driver. So what happens there is that we generate all the instructions. It's a really assembly, let's say ARM assembly looking language. We generate all the instructions to actually process a full triangle and in the pixel pipeline and then put that to the compiler so that we can get rid of all the different states that just don't affect this one. So that if you're using def test, let's say less or greater or whatnot, you can just put that specific comparison instruction into the instruction stream and then at the end put it through the full compiler pipeline and get the fastest possible output that you could possibly hope for. And well, of course, because we know what the problem is, we know the structure of our programs really well because they're always the same triangle processing, pixel crunching pieces of code. We really could tune our compiler so that we're actually getting better results than any of the compilers that we've compared it against, like MSVC or GCC. And of course also better than what you can accomplish by writing everything by hand, which of course is impossible task as there are something like, I don't know, maybe 1 trillion of different possible states that you could be in. Here's actually a screenshot of one of our test applications, and in the middle you can see the window displaying some disassembly output, which is this piece of code has been generated on the fly, and it's still in the intermediate format which was produced out of the what we call the pixel pipeline generator, and it's just waiting to get passed into the compiler. And actually in this particular case, this one gets compiled into ARM code, even though it's running on a PC, as you can probably see. And it's getting emulated, and every single pixel that we draw, we actually emulate that sequence of code using our own ARM bytecode emulator. Handling floating points is another tricky issue because, as I said, there aren't no FPUs present on most of the devices. This is also starting to change a bit, but well, a majority of them still don't have those. And the libraries that you get with your platform are typically so slow that they just aren't really usable, and that's due to many reasons, like, well, they just have to implement all the infinity handling and not a number handling properly, whereas we just don't, because we are only interested in getting the pixels on screen. The specifications explicitly say that you don't have to handle those things because the game's already lost at that point if you get an AND inside the pipeline. And we cannot use fixed point math purely because we are implementing the common profile of OpenGL ES, which specifically states that you have to have something comparable to the IEEE floating point spec. So again, we had to have a bag of tricks to actually make it fast. And well, naturally we try to use fixed point whenever possible. Like for instance, the whole triangle rasterizer, like after the so-called vertex pipeline has been executed, that's fully in fixed point. There are some other things, for instance, in the lighting pipeline where you can use fixed point without the possibility of overflows if you kind of pre-processed your matrices properly and so forth. And another thing is pseudo-floats. We have something like maybe a dozen different floating point vector and matrix and scalar data types inside our implementation, which are all fine-tuned and customly tuned to the given situation in which they are used. Like we have a specific format for storing vertices in clip space, and for doing lighting we have a different format, and so forth. 64-bit integers are used for robustness, mostly in the rasterizer itself. And of course there are places which just aren't that critical in sense of time, and there you can just use some. Well, we have our own floating point emulation library, and we're using that because we're getting better results than on most platforms, and it's more predictable. But at some point it doesn't matter. You just don't need to be that fast, and there it's easier to just pick the easy way out. Yeah, this is a bit hairy. It's actually just one 64-bit shifter operation that we have implemented. And the reason why it's so hairy is that we really wanted to get the optimal code out of that. I mean, on many compilers we've seen that, for instance, in some cases you should be able to compile this into 2 or 3 instructions, depending a bit on what the shifter value is and so forth. But it's not very untypical to see actually compilers produce something like 20 or even 30, which is a 10-fold increase instructions produced if you use kind of like the compiler's own native 64-bit type. So that's why there's more or less a single variant for each CPU and compiler combination that we are actually using. And it actually continues something like 2 or 3 pages down. So also, it's pretty costly for any device manufacturer to actually put any kilobytes of code onto their device. It's really expensive. So we really had to pay close attention to actually cutting down the library size that we have. And one of the basic tricks that you see is to split your code into fast and small parts, where you use, let's say, different compiler flags for the 2 parts. And in case of ARM, you want to compile the fast code into ARM code and the small code into thumb. The thumb code typically runs slower, but you just want to use that for the parts where it doesn't matter. And besides, it's not that much slower. And also, if you want to do dirty tricks, it's a nice way to actually put those tricks into really small inline functions that you call from all over your code, so that you don't get those dirty tricks corrupting your code base everywhere, but instead you do the small changes in the inline function itself, and then if you save even one instruction in that particular function, it might easily mean 100-fold saving somewhere else because it's called so many times. But you definitely don't want to do the tricks everywhere in your code base. Also, memory is a really scarce resource on a mobile phone, and we have to be careful about not really making any allocations unless we just have to. Same goes for stack. This all sounds really simple on paper, really. I mean, we could write a toy implementation in probably something like 2 weeks, which could pass the conformance tests and mostly comply to the rest of the spec as well, which isn't tested by the tests. but still the different constraints that we are facing make it really difficult. And it took us 5 years or 5 man-years to actually accomplish or finalize the project. And it's probably been the most challenging project that I've ever been working on. Some of the most tricky areas, like, I don't know, I personally consider it maybe the hardest programming problem in the world is to build a robust clipper, and emphasis on the word robust. I mean, we've been finding bugs from our clipper like time and time again, and it took me something like 1.5 months to actually get it work. And it's of course, it's trivial to get a toy clipper to work as well, one that doesn't fail in typical cases, but once you start giving it as input values which are all close to, let's say, floating point maximum, or then like really close to 0, and you end up in a situation where like 1 bit variance in your clip factor computation can actually throw the produced vertex something like, I don't know, 3 frustums or 3 size of a frustum to the left or right. You actually start getting into trouble, and it's been really hard to get that to work. But I believe currently it does work already, but I cannot be sure still. And another things that are pretty tricky are gradient setup. It's really easy when combined with imperfect rasterization rules to actually overflow some of your gradients. And these are again things that you don't see or in many games, but if you want to make a high quality implementation, you really have to pay close attention to getting this right. So that's about it. Thank you for following through, and if there are any questions, I'll be happy to answer. Plus, I'll show you a small demo. And also, I have a one phone demo phone with me, and I can show the SP mark running on that one as well for those interested. Thank you.
One question. Do you have sort of thoughts about OpenGL ES 2.0 software implementations? Does the fact that it's sort of programmable shaders only make it more difficult, or is it still feasible to do a pure software ES 2.0?
I think it's very well possible. The question was that do we think that is it possible to build OpenGL ES 2.0 with all the programmable shaders actually in software as well? And we do think that it's possible because we already have much of the compiler technology in place in our 1.x stuff, which could handle similar things like the shaders that you get as input from the OpenGL spec. Any other questions?
One question. Did I understand correctly that when you change the state of the OpenGL state machine, that you run some kind of compilation before you get the final pipeline in your current implementation? So does it make really slow to change, for example, you said the depth comparison mode? Because you have to run each time you change the state, you have to run an instant compiler.
Well, the question was that do we always, when the user changes some OpenGL state and calls the draw elements or whatever, do we always have to invoke the compiler and everything? And the answer is yes and no. Of course, all the states that don't affect the pixel pipeline, those we can just discard and keep the pipeline that we've already compiled. And in other situations, the answer is typically yes for the first frame when we cache all the compiled results. And then on the subsequent frames, we just go through the cache and see if that given loop is already compiled and optimized and so forth. And in that case, it's really fast. The compiler itself takes something like, I don't know, maybe depending on quite a lot on the input, but in the order of from couple to, let's say, 20 milliseconds typically. Any other questions? Okay, thank you.